In the last class, we looked at the different chemical exchange processes. We saw that there is what is called slow exchange and fast exchange, and the slow and fastness of this exchange is based on the chemical shift difference between the peaks. So, therefore, we say that the exchange is fast or slow on the chemical shift time scales. But that is not only the chemical shift time scale that is important. We can also characterize a chemical exchange based on another time scales, that is of relaxation time scales, or we can also call it from the diffusion time scales. So, this is what is shown here, that we can use other NMR parameters such as T2 relaxation, diffusion, etc., which can also be used for monitoring chemical exchange. Because what may happen is, in certain systems your peaks, the chemical shift which we need for the two different states A and B, that chemical shift information may not be available. So, it may not be possible to measure the chemical shift of state A and state B, and therefore, we may not be able to characterize the dynamics from the chemical exchange chemical shifts. So, in such type of systems, we will then have to go for the T2 relaxation or diffusion. So, this is how what is shown here, that we can also look at these different exchange processes based on these criteria. So, we can say that an exchange process rate of exchange, chemical exchange, is slow if it is much smaller than the difference in the relaxation rate between the two states. So, here we are measuring 1 over T1, not T1 direct, T2 directly, 1 over T2, because 1 over T2 is a rate, and that is what is, this is also a rate. So, the exchange rate is very slow if it is much smaller than this difference in the 1 by T2 of the state A and the state B, which we are trying to characterize. And as we saw in chemical shift case, we say that this is intermediate exchange if the exchange rate falls almost similar range as the difference in the relaxation rates. And we can say that it is a very fast exchange if the exchange rate is much higher than the difference in the relaxation rate. So, we can see here that based on this relaxation properties, we can characterize whether an exchange is fast or slow. Similarly, we can do it in the, if we have the diffusion rate for the molecule. So, this is the translational diffusion rate which we are looking at here, and we will see later in the next part, in the next class, how it will happen. But let us continue. Suppose we know that there is a diffusion rate available to us, translational diffusion of the two states A and B, and we characterize the diffusional rate by using a constant known as diffusional rate constant for that state A and state B. Then if the difference between the two is much higher than the exchange rate, then we say that exchange rate is a slow process. That particular chemical exchange is slow. For example, this can happen, let us say you are trying to study the exchange between a monomer and a dimer of, let us say, a molecule. And if there is an exchange between these two states, that is monomer and dimer, then we can characterize that by an exchange rate, and that is slow or fast will depend on the difference in the diffusion between the two. Okay. Now, we can say that there is intermediate exchange if the exchange rate between the monomer and dimer, again for example, comes very close to the diffusion difference in the translational diffusion coefficients of the two states. And we can say that the exchange rate is fast if the translational diffusion between them is much smaller than the exchange, that is, exchange rate is faster than the difference in the translational diffusion rates. So, these are also the other parameters which we can use for characterizing the slow exchange regimes. So, we use the word regime based whether it is a slow exchange regime, intermediate or fast, not only based on chemical shifts, but also other parameters. So, this when you use other parameters, then we have to measure them by some methods. So, for example, T2 exchange can be measured by different experiments which we will not go into detail in this course. Similarly, your diffusion rates can be measured by what is called DOSY, which we will see in the next part, and so on. So, therefore, we can also use not only chemical shift, but also the exchange rate. But one thing you have to keep in mind is that a particular exchange, let us say a fast exchange, on the chemical shift time scale may be fast, means it may fall in this particular regime, and you can say that in the chemical shift time scales they are fast, but it may be slow on the T2 time scale because it may come into this condition. So, it is not that if something is fast on chemical shift time scales is also fast on relaxation time scales or vice versa, it all depends on these differences. So, our exchange rates becomes accessible based on what we are trying to measure. So, now let us to note the next topic, which is the again based on chemical exchange, is what is called hydrogen deuterium exchange, HD exchange for in short. And this is a very routine experiment measurement which is done on many peptides and proteins, because it helps us to tell whether that particular hydrogen is involved in a hydrogen bond or is it exposed to solvent and so on. So, what is done in a hydrogen exchange? We do the following. You take, suppose this is a molecule and this has a hydrogen atom attached to it, we let us call it as chemical shift delta A of that hydrogen. Now, this molecule solute will be dissolved in a solvent. So, suppose solvent is a protic solvent, means it has a hydrogen which can be exchanged, and that hydrogen, let us chemical shift of, let us call it as delta B. So, this will be for example water or methanol, it is all the protic solvents. Now, what will happen is, if suppose there is an exchange between the two, that is the solvent hydrogens and the molecule hydrogen, this is typically happens in peptides and proteins when we dissolve in water. And what are those hydrogens? Typically it is the backbone amide hydrogens we are going to look at. So, the backbone amide hydrogen NHCONH, that NH is called a labile hydrogen because it is exchangeable with this hydrogen of the solvent, and this exchange now is a reversible process. It goes and exchanges with the solvent. So, you can see by the color here that this hydrogen which is black comes to this now, and it has come to the molecule. So, it has got now this chemical shift, but this hydrogen which was on this molecule has migrated to the solvent and it has become a different chemical shift. So, therefore, there is a constant interchange between these two hydrogens, and that is a reversible process, and we can call it by we can denote it like K1 and K minus 1. So, this is again the similar to or same as the chemical exchange process which we saw earlier. So, now why is it useful? Why is this experiment useful? This is a few reasons are given here. So, one of them is that when you characterize this exchange is very useful, such as we discussed for hydrogen bonds, ligand binding and so on. So, for example, let us say that there is a very slow exchange between them. That means these two hydrogens do not exchange rapidly, very slow. Let us say it could be even hours or days. That means in 1 hour it may exchange only once. So, it may be very slow exchange, and why is that is very slow? That is because this hydrogen may not be available for exchange, and that is what is written here, that it is protected from exchange because for either because of two reasons. One is it could be because of hydrogen bonding, that is this hydrogen is bonded to some other hydrogen some other oxygen in the molecule, and therefore, it is tightly protected, it cannot be released for exchange, or it could be that this hydrogen is buried inside the molecule, deep inside the molecule, for the solvent molecule cannot penetrate or this cannot come out of the molecule to exchange. So, therefore, that could be another issue, a reason why the exchange can be slow. So, when does this kind of a protection from exchange happen? Suppose let us say you are studying a protein folding process in which the molecule is a linear molecule, a linear peptide starts to form a tertiary structure. So, let me schematically show you by this picture drawing here. So, suppose I have a linear peptide like this, and when I start folding it or when it starts folding in an environment, it may form now a secondary 3D structure, tertiary structure. So, during this process, suppose there is a hydrogen atom here, that hydrogen atom comes here and it maybe it gets protected and it comes into the system inside the structure. So, therefore, it becomes protected. So, here we can say it is exposed. So, it will be fast exchange, means it will exchange rapidly. but here it is protected. So, we can say it is slow exchange because it is not available to exchange. So, this can happen during protein folding. So, hydrogen exchange therefore, is a very popular experiment to study this folding process, and we people look at how this hydrogen exchange rates, chemical exchange happens between solvent and the proton during this process. So, this is important. Similarly, you can also have a situation where a protein or a peptide or a molecule is aggregating, means it is forming oligomer, dimer, trimer, tetramer and so on, and during that process the hydrogen which is exposed in a monomer may start now getting buried because it is now in the interface. Interface means between the two dimers, it is forming in the interface between monomer and dimer, between the one molecule and another in the dimer. So, it now gets protected from exchange. So, that also can result in a slow exchange from fast. So, initially it is fast because it is monomer, but it becomes a dimer or trimer, it may become slow. So, therefore, that also helps us to, hydrogen exchange helps us to characterize this aggregation process. And typically the protons, as we discussed, are the one which we are studying are the NH protons and the OH protons. OH is a side chain protons in the case of serine, anthraquinone and so on, tyrosine, but normally they exchange very fast. The most standard protons which we use for this characterizing this hydrogen deuterium exchange are this NH exchange, backbone amide, they are called exchangeable hydrogens. So, let us see how we characterize this exchange. We use this word called protium deuterium exchange. So, here what we do is we take the molecule again which is shown here, but this time we will use a deuterated solvent. We use a deuterated solvent. The reason is that when the hydrogen exchanges with deuterium, which is as shown here, then this the molecule, the deuterium comes to the molecule and hydrogen has gone to the solvent. This, because of this deuteration, we use the word deuteration, because of the deuteration the signal from this hydrogen is gone. That means, the chemical shift delta A which was coming from here, the peak now it disappears. Why does it disappear? Because now it is replaced by a deuteron. So, therefore, because of that the signal is lost. So, the more the exchange takes place, more is the signal lost. So, we can actually monitor the loss in the signal intensity of the molecule of this hydrogen and with time. So, as it is reducing with time, it means it is exchanging with slowly with time. If it does not exchange at all, if it is very slow exchange, then this hydrogen intensity will not reduce and it will be almost constant or very slow decay. But if it is exchanging rapidly, it will decay very fast. So, based on the decrease or decay of the intensity of this hydrogen signal, we can characterize its exchange, whether it is a slow exchange or a fast exchange. So, this is what is written here, that when we expose the molecule to a deuterated environment, the exchangeable protons will start exchanging, and because of the large excess of the solvent. So, this, remember, this is a millimolar, a very less, whereas solvent is in molar, very high. So, the molecule's protons now are slowly replaced with deuterium, and therefore, the proton signal starts disappearing or reducing in intensity due to the deuteration. So, therefore, as the signals disappear in terms of the intensity, they decrease as a function of time. That can be monitored, and if it is slow, we can measure up to a long time, but if it is fast, it has to be done rapidly. So, this is typically the profile which we will get, that the intensity of that hydrogen atom which you are looking will slowly decrease with time, and this is typically an exponential decay, and that can be fit to a exponential decay equation like this, the intensity. So, intensity is measured at various points. So, you may have intensity measures at, let us say, initially 0 before you put it. As soon as you put it, you may have intensity here, you may have intensity here, you may have measured here, you may have measured here, you may have measured here and so on, and after this it is almost 0. So, by measuring this kind of a large number of intensity points in between, we can actually characterize we can measure these points and fit it to this equation, and from that equation we can extract the exchange rate K exchange, and that is very useful because if K exchange is slow, we can say that it is protected, and if this is fast, we can say it is exposed. So, there are a lot of methods which are known in literature to measure the exchange rates. So, typically this is how the experiment is done. The experiment is carried out by dissolving the molecule in D2O, 100% D2O, and then a series of spectra are collected at different time intervals. So, every 5 minutes or 10 minutes you measure, and then as we saw, you fit that decrease in the intensity to this particular equation to measure or obtain the exchange rate. But what is the limitation of this approach? The limitation of this approach is that as soon as you dissolve in D2O, the protein will, the spectra has to be recorded. Why? Because as soon as you add the D2O to the sample, all the NHs will now start exchanging with the D2O. So, if there is a very fast exchange, by the time you record the first spectrum after dissolving, your signal would have been already gone to 0, because that exchange would have been very fast for that proton, and that proton will be completely absent, disappears from the spectrum. So, when it goes completely absent, you cannot measure this profile because you do not have any intensity measurement. So, that is the big drawback. So, we have to increase or speed up how we do this, and many protons exchange rapidly with solvent. So, that is why this typical standard method does not work. And what is the limit of this method? The method typically works if your exchange rate is 1 per second. That means, if the hydrogen and deuterium in the solvent exchange 1 per second, 1 time per second, once per second, less than that means if they less than once per second, then you can say that that exchange is slow, and that can be measured by this kind of approach. But if your exchange rate is faster than that, then you cannot use this approach, and there are many alternate methods have been proposed to measure exchange rates faster than 1 per second. So, we will not go into that because that is a more difficult, more research oriented work, but the one should keep in mind that exchange rates, slow exchange rates can be only measured if you use this approach where you just dissolve the molecule in 100% D2O and you monitor with time. So, this brings to the end of this hydrogen exchange part. We will now move on to the next part of this advanced lectures in NMR course. So, this is the next topic is what is called diffusion order spectroscopy, or in short DOSY. So, DOSY is a very standard technique, very useful technique used in chemical research, in analytical chemical research for characterizing different compounds, and so few of the applications are listed here. So, typically we measure diffusion if you want to characterize the mobility of compounds. So, what is mobility? We are now talking about translational mobility, not rotational, and the rotational diffusion is another type of diffusion, translational diffusion is another type of diffusion. So, our experiments, all these experiments under the word DOSY is based on the translational diffusion of compounds, and this method DOSY is also useful for studying binding of small molecules to proteins, because small molecules have a very fast diffusion, they diffuse very fast in the sample, but when they bind to the protein, their diffusion is now reduced, because proteins are big molecules. So, they are heavier and they do not diffusion is very slow. So, by noticing the change in the diffusion, we can characterize the binding, and this is one of the standard approaches used in drug discovery, where they also use the word affinity NMR, where they are screening a large number of molecules to proteins for a receptor or a target. Suppose this is a target protein against which you are trying to develop drugs, and you are screening compounds, the one which bind to the drug, the one which binds to the protein target strongly will diffuse slowly, and the one which does not bind, they will diffuse fast. So, by like this method you can screen or find out which of the huge number of molecules we have, which of them actually bind to the target protein. You can also identify individual compounds in a mixture. Suppose you are given a mixture of compounds and not a pure compound, and in that case each compound may have a different molecular weight. So, but looking at the 1D spectrum, you cannot tell which molecule is which peak. because they may be similar and in the same range, and there is no connectivity information in 1D. So, you can either do 2D NMR or you can also do DOSY, in which it helps you to separate in the terms of spectra which compounds are diffusing faster, which compounds are diffusing slower. So, that way you can identify compounds from a mixture. Another very useful application of DOSY is for studying aggregation of molecules. So, let us say I have a molecule which is undergoing aggregation, for example, forming amyloid or so on. It will go from monomer to dimer to tetramer and so on. So, at each stage it is becoming higher and higher in molecular weight, and at each stage therefore, it is becoming slower and slower in diffusion, translational diffusion. So, therefore, by monitoring the diffusion coefficient at each stage of the process, I can figure out whether the molecule is a monomeric state or how it is going, whether it is going to dimer or is going to trimer and so on. So, aggregation processes very nicely can be monitored with DOSY. So, now let us see how the DOSY experiment works. For this, you have to understand what is called gradients. So, this is what we have seen in the very first part of the course, where we looked at how the hardware aspects. When we looked at hardware aspects, we had a quick look at what is called gradients. So, basically gradients are like coils like this, which is located in this part of the probe. So, this whole thing here is a probe, the probe which goes into the magnet in the central portion of the magnet, and this probe has a RF coil here, you can see in black color, which is the coil for pulsing and receiving signals from the sample. But on the top of this coil, up top and bottom, you have this another circular coils, which we call it as gradient coils. Now, what are gradient coils? Gradient coils are nothing but you apply a current in this coil. So, whenever there is a current in this coil, remember a magnetic field is generated in the center of the coil. This is the standard laws in physics, that when a current flows in a coil in perpendicular direction, there is a magnetic field generated at the center. So, if I flow it in a clockwise direction, I will get this direction. If I flow current in this coil in a opposite direction, anti-clockwise, then I will generate an opposite magnetic field. Okay. So, this is how we do that, and here you see this is the main magnetic field, main meaning the big magnet which is outside, which is where probe is sitting in the magnet, and that is the big magnet P0. And this magnet field, which is generated by putting current in this coil, is a very small magnetic field, very small, and it is in the milligauss, millitesla level, whereas this is in the Tesla scale. So, you see this is 1000 times less, and that is a very small magnetic field, but what is happening now is I am applying this current here. So, my sample will be sitting in this coil. So, then it will experience a additional magnetic field on this direction towards the top. This is the top part of the sample, whereas the bottom portion of the sample will experience an opposite magnetic field, because now it is now subtracted from B0. So, this is like a chemical shift type of a thing, where the molecule at the top have a different chemical shift, because they are now B0 plus B, because they are now in the same direction, and molecules sitting at the bottom of the sample have a different chemical shift, because it is B0 minus B, because it is opposing the main magnetic field. So, the whole idea of DOSY relies on this gradients. We can only do DOSY if we have gradients in our spectrometer, and nowadays all modern spectrometers have these gradient coils. So, it is not a big problem to do DOSY experiments on any standard spectrometer. So, let us see again this concept, how this affects the sample. So, this is what is shown here, that I have now shown a sample here. This is the sample tube, and what happens is typically you have what is called an effective sample volume, means your sample which is sitting here, this portion of the sample is what is effective, because all your coils, RF coils is here, your gradient coils are here, and above and below has no effect on the sample. So, our main focus will be on this rectangular portion of the sample, which is exposed to this gradient coils. So, this is what is shown here. Now, as I said in the last slide, because of application of this magnetic gradients Now, the magnetic field at this portion, that is the top part, these are the molecules shown here, 2 molecules let us take, one at the bottom of the sample, one at the top of the sample. Now, these 2 molecules do not have the same chemical shift or the precessional Larmor precession. Why? Because at the top portion of the sample I have added an extra magnetic field which is given by G into Z. Why? What is Z? Z is the distance from the center. So, at this point it is a maximum, and it is now the chemical shift of that molecule which is sitting here is now a slightly different value compared to the original omega naught equal to gamma b 0. So, we have a addition of a magnetic field. Now, if you look at the bottom of the sample, it is opposite. Remember, we saw in the previous slide, it is opposite to the main magnetic field. So, I can say it is subtracted. So, it is my, and what happens in between? In between it is a range of values. So, for example, if you look at the center, this up magnetic field cancels the down magnetic field. So, at the center the magnetic field because of gradient is 0, but this is still there B 0. So, at the center the chemical shift will be omega equal to gamma b 0, there is no G and Z, no G, Z is 0. Now, center means Z is 0, but if I go down towards this side, then the negative magnetic field dominates. If I go towards top of the sample, the positive magnetic field dominates. So, therefore, we say that we have created a gradient. This is why we use the word gradient coils. We have created a gradient of a magnetic field. So, the magnetic field is no longer across the sample. We have purposely, deliberately created a difference, and that is the gradient, linear gradient, and this is along the Z axis. Okay. So, this is along the Z axis we have created this gradient. Now, this gradient what it does? Now, if I apply a pulse to this sample, then the sample, the magnetization as we saw comes to this direction, xy direction when I apply a pulse. Now, when after the pulse, when I apply this gradient, these 2 currents in this coil, then the molecule which is here will have a different chemical shift compared to the molecule which is here. So, all the molecules now do not have the same chemical shift. Remember, they are the same molecule, but because of this change in the magnetic field across the sample, the molecules here will have different chemical shift compared to here, compared to here. So, therefore, they will now start rotating or oscillating with different chemical shift. So, very similar to what you saw in the T2 situation, the T2 also, because of the local magnetic field fluctuation, the T2 we saw that there is what is called dephasing, but here also there is dephasing, but this dephasing is not because of T2, it is because of the difference in omega naught, and that difference in omega naught is coming because we have purposely created a difference by applying a linear gradient, and that is shown in this picture here. There, that is completely dephased. So, after some time, suppose I keep the current on in this coil for, let us say, for few milliseconds. Typically we apply this current for a very short duration, it is about 100 microseconds to 1 millisecond. In that time the molecules completely get dephased, and same molecule which is the same chemical shift before, but now because of the gradient has now acquired a range of chemical shift along the sample and has completely gone in all directions, and it is dephased. So, that means if I now record a spectrum, I will not get any peak at all. Why? Because complete addition of this is 0. So, let me point out that this is in the xy plane. So, this is, let us say, x axis and this is y axis. So, in the xy plane the signal is 0. So, this is called complete dephasing of the magnetization. So, we will see in the next class how now this can be used for measuring the diffusion of molecules, and how this will be very nicely we can calculate how the molecules are translationally moving in the sample.